So you're very welcome to the second session of the session in complex and algebraic geometry, and I have the great pleasure to introduce our first speaker, Chenyang Xu, I guess, from Peking University, moving to MIT very soon, and he will speak about interaction between singularity theory and the minimal model program.
Thank you very much. So first, of course, I want to thank the ICM committee to give me the honor to speak here. So let me start to introduce some concept in my title. So if I start with a singularity, so singularity, you can just, if you don't say it before, you can just think about it at some point with some algebraic geometry structure, but it's not smooth. Then the first thing you might think about is you just find something which I call it a y mapped to x, such that the y itself is smooth, and there exists a lower dimensional subspace z in x, such that this map from y to x is isomorphic over x minus z. So if you think about it, I have this kind of space. It might be singular along some part. Now I just pick up a y mapped to this x, such that on this singularity, I might do some change. But in the large open set, which there is not, which the x is smooth, the morphism from y to x is just the same. Now, for such kind of morphism, that there are big open sets both in x and in y, they are identical, but they might differ along some lower dimensional set. For such kind of morphism, we call it birational. So if it's your first time to say this kind of thing, you may naturally wonder why the birational is a good notion. So the main reason for birational to be good notion is in algebraic geometry, it's very sensible to study those functions which are defined everywhere except along some lower dimensional set. So this kind of function we call regular function or meromorphic function. So basically x and y, they are birational if and only if they have the same set of meromorphic function or regular function. So in other words, to study x and y up to birational morphism is the same as to study the meromorphic function, and it forms a field. So then in characteristic 0, actually the dream which I stated in the first step, it can always come true. That's because of this Hironaka's resolution of singularity theorem. So for such a singularity, you do be able to find a y satisfy the properties. But on the other hand, when you deal with dimension larger than 2, so starting from dimension 3, the resolution of singularity, usually there is no the best resolution. I mean, you can think about it. If I have one resolution, y to x, I can just start to blow up y and more. So I can easily produce like higher and higher resolutions just based on one given one. So if there is a best resolution, in some sense it has to be minimal. So it cannot be, you might expect that all other resolutions should dominate it. And it happens in dimension 2, but not a dimension higher. So in other words, we want to find kind of more canonical, we want to find models with more canonical properties. So there is another set of ideas to produce different models if I start with, say, a smooth model. So this is something called a minimal model program. So in other words, I mean, roughly speaking, when I start with a smooth variety X, I just produce a sequence of birational models following some algorithm, like from x to x1 to x2, until I stop with a model with more canonical properties. So minimal model, you can think about it, it's an algorithm to start with one model to produce a bunch of models, but end up with something called a minimal model, which has canonical property. So in dimension 2, this works very well. I mean, you start with any model, you take a resolution, then you just start to run minimal model program. You always get at the end, get a smooth minimal model. So this was known like more than 100 years ago by the work of Italian school. But one very important conceptual observation in higher dimension is that I think in late 17th, early 18th, Morey and Reid, they realized that when the dimension is at least 3, if the minimal program can be run, actually you always have to deal with singular varieties. So there is no way you just run the minimal program among smooth varieties. Certain singular varieties has to be introduced in. Nevertheless, the singularities appear in this process is not random. It can be controlled by some invariants, which I will introduce in the next slides. So then it's very natural, if I want to get a better knowledge of minimal program, I have to understand this kind of singularities. So I think this is the starting point for us for people working on minimal program to think about this kind of singularities because we really want to get better knowledge about the minimal program process. But later it turns out these singularities we defined for running minimal program, it actually naturally arises in many other contexts. So for instance, it arises in study of Canonical metric. It also arises study in Frobenius action and mirror symmetry and so on. I mean, you will see in my talks that some of the different topics which these singularities arise unexpectedly. Anyway, in the development of the singularity theory in minimal program and the global geometry, actually they are just intertwined. So in this talk, I will basically talk about 3 interactions between the singularity theory and the global geometry. I mean, by no means this is a thorough treatment. Actually, in 2016, Collard published a book called Singularities in Minimal Program. And all the 3 themes are kind of after the book was published. So it's kind of more recent, but even that, it's not, I don't claim this is the treatment of all the recent development in this theory. So the theme 1 is, this is kind of classical. So given a singularity, I think people just look at the link, which if I embed my singularity X into some big affine space, I mean, my singularity is local, so I can always embed in some big affine space. And then I choose a ball here around the singularity. I take the intersection with X minus X. So this is called the link. So sometimes people take the sphere, sometimes people take the ball. And so this is a very classical way to study singularities. Actually, by Milner's work, we know this link carries all the topological information of the singularities. So it's very important to study it. And so we will talk a little bit about how to use partial geometry to study this. And also it's non-Archimedean analog. So this is the theme 1. So the theme 2 is, we study this kind of question. So for holomorphic function f, so which I consider that the C, which is defined in this way, it's a lim sup such as 1 over f power to 2c is locally integrable. So I think this kind of invariant first appear in the study of oscillating integral, but in the real case. And people soon realize the holomorphic version is actually very interesting. And so we basically want to study the properties of the set of all such C when we fix the dimension n. And particularly, we want to talk about the Shawcroft's conjecture, which is called ascending chain condition conjecture, which I will talk about later. The theme 3 is, I mean, actually, I want to ask that whether there is a stability which we can talk about around the singularity. I mean, there's first sounds to be kind of very far from the reality, because usually the stability is for the global geometry. But actually, I want to say there is a deep theory around a large class of singularities we are interested in, and which we can talk about the stability. So, okay, now let me just go to the define what kind of singularities which I want to study. So let me say I have a normal space X, and I assume it's pure Gaussian. I mean, this is a technical term, but by definition, it just say the class group of K, the canonical class, is a torsion. Is torsion. So in other words, some power of this Kx will become Katia. This Kx itself is always a Wave divider, but now we require some multiple, some positive multiple of it will make it to be Katia. So Katia just means locally it can be written as a function. So now I consider resolution, which I know always exists by Hironaka theorem. And I actually require that the exception set, so this just means a set which the F is not isomorphic. So remember, F is isomorphic on a big open set, but it's not isomorphic along some lower dimensional set. And I just call those set which as an exception set. And I just want to assume that the exception set is simple normal crossing. So in other words, locally it's just given by a bunch of coordinates in the analytical neighborhood. And this, again, this can be achieved by Hironaka theorem. And now I just write the relative canonical class. So basically I pull back the differential form, the highest differential form on X. And then if you take the Jacobian formula, change the coordinates, you know there will be some terms in front of the dz1 to dzn, and those like variation, the variation locus of this Jacobian formula is given by this formula that the ky over x is the sum of ai x ei. So this number ai we call it discrepancy. So basically this formula I just use it to define the discrepancy function of this x, and it's defined for every divider, which is in the exception set. Because I mean ky over x, I mean only the difference between x and y is only along the exception set. And now by looking at this number, I define certain class of singularities. So if it's always positive, that for every EI, it's called a terminal. And if it's non-negative, it's called the canonic. I think historically, those are the first two class of singularities people studied. But then, as you will say, later we will start to study the pair version. And then for that, it's better to study whenever it's larger or larger or equal to a -1. So that's how we introduce the Kawamata log terminal, which I will just write it as KOT later, and also log canonic. So the difference between the first two and the second two is I just look at whether it's larger than 0 or larger than -1. And of course, the important thing is that each class of the singularity is preserved under the minimal program. So again, if I start with a smooth variety, I don't know. Usually it's not, the smoothness is not preserved under this minimal program. But since smooth variety is terminal, and I know the terminal singularity is preserved under this minimal program. So particularly I can conclude, if I run minimal program start with a smooth variety, in each step I got terminal variety. So this is, I think at the beginning why we study this kind of function, because on the minimal program, it only monotonically increases. So on the other hand, once beyond dimension 3, basically it's too complicated to give an explicit classification of all these kind of singularities. I mean, in dimension 2, terminal is just smooth, canonic is just ADE, and the KOT is just quotient singularity. And the log canonic, I mean, you have to make a little bit of more work to classify all the log canonic singularities. But we are able to classify all of them. And also, but that's actually not very hard to classify in dimension 2. Then in 80s, people spend a lot of time to classify the singularity in dimension 3. And by that time, I think people concluded that there is no way to make an explicit classification when dimension is larger than 3. Also, this was what I just said. We can just define similar notions, not for just x, but for a pair x delta. And so similarly, we just define this discrepancy function, and we define the class of singularities based on this. And this kind of extension from a single variety to a pair actually will give us lots of flexibility. And I think this was realized also in early 80s in minimal program theory. So, okay. So here, so now I come to the first theme. So remember that the minimum program usually it's not smooth, but it has some canonical properties. So here we can apply the similar idea into the revolution. So let's say I start with the revolution. I run certain kind of relative minimum program. Then usually I don't end up with a revolution, but I end up with some model. It has some canonical properties. So now instead of revolution, I just want to look at this kind of models. So that's what we call Deity Modification. So the technical definition is if I have one Kilgrosson isolated singularity, I can take the revolution and run this relative MMP. And what I end up with is a model which I denoted as XDLT, such that if I take all the exceptional divisor of this map, and this pair XDLT delta is the Rory log terminal. So it's slightly weaker than Kawamata log terminal. But we can define it in this way, that there is a simple normal crossing open set U, such that if I restrict my pair on this U, it's simple normal crossing. But then it's not a simple normal crossing everywhere, because if it's simple normal crossing everywhere, that's just a revolution. But as I said, usually after we run MMP, it's not necessarily a revolution. But then there will be some singular part. However, it has the properties that if I have a divisor whose center is on the singular part, so it's on this part, it's outside this simple normal crossing part, then the discrepancy function is always larger than -1. So in other words, this is the definition for KLT. So in other words, there is a simple normal crossing part, and outside the simple normal crossing part, it looks like a KLT. I mean, roughly speaking, you can understand it this way. And again, but what's the canonical property? The canonical property is that this gadget, this log canonical class is always nef. So that just means the intersection of this class with any curve C is non-negative, such that when the curve is vertical over the x. So if you take an arbitrary revolution, this condition usually doesn't hold. This condition precise means it's a relative minimum model. So this condition is basically guaranteed by the minimum program. And so what I mean by canonic, so usually even this kind of model is not unique. But however, if I have two such kind of models, if I take a common model which dominates both two these models, then the pullback of this low canonical class are the same. In other words, they are kind of like the same low canonical class in the bidirectional sense. And this is the canonical properties which I want to talk about later. Now, basically, out of the information of this Deity modification, we can define a regular cell complex, D delta. Basically, this complex characterizes how this EI intersect with each other. So the definition is for each EI, I just take a vertex, put a vertex there. Then if I have one component of EI intersected with EJ, I just draw an edge to connect them. And then if I have three of them intersect along some component, then I just put a two-dimensional cell corresponding to this component. And I just keep doing this until I capture the highest intersection. So then it's very easy to see the dimension of this dual complex is at the most dimension of x minus 1, because there are at the most dimension x of them to intersect at one point. And so then it's a proposition proved by Durford, Nixon, Kohler, and myself that if so for different choice of the Deity modification, indeed this dual complex is always the same. Because, I mean, although we may have different Deity modifications, but because when I choose a common model, when I pull back the low-canonical class, they are the same. So that canonical property implies that the D delta, actually, this dual complex doesn't, the PL structure of this doesn't depend on the choice of the Deity modification. So then we can just give a notion of this, which is, I call it DMR, X in X. So this is out of the Deity modification. I mean, you may wonder why I just don't define this for resolution. So if I don't know minimum program, I only know resolution of singularity. I can define a similar gadget but only for the resolution. Actually, people do that. So actually, I can take a local resolution and define this dual complex for this resolution. But the disadvantage is that if I define that way, actually, it's not unique up to homomorphism. Actually, people can prove it's unique up to homotopy. But it's not a homomorphism invariant. It's only a homotopic invariant. But Berkowitz and Tahulier, they actually prove that the non-commuting link, which is a subspace of the Berkowitz identification of this singularity, indeed has a strong deformation retract to this dual complex, which is defined out of this local resolution. So the local resolution has this good property that it basically captures all the homotopic information for the non-commuting link. And the theorem proved by Durfin, X, Kohler, and myself is that indeed this invariant, which is well defined up to homomorphism, actually has the same homotopic properties as this one. So this one, I mean, as I said, it's not well defined up to homomorphism, but now it's only defined up to well defined up to homotopy. But actually, this way we construct a canonical representative of this invariant. So somehow this kind of idea is actually more interesting when people to study the degeneration of smooth varieties. Although the entire proof is basically the same. So if I start with some like minimal varieties over a puncture disk, and now I just close up my disk. I close up my variety to get a minimal DLT model over the disk, and then I just can take the dual complex of the special fiber of my closed-up family. And Nikes and myself prove that if I start with this X, which is a Calabi-Yau, and then our definition, which I just take in the first step, is basically identical to the definition of Conjecture and Soilman, which they call essential skeleton. So, but if you look at their original definition, it's kind of they just define an abstract subset of the Berkowitz space, the Berkowitz identification of X. And now we just basically realize this abstract defined subset as a dual complex of some model, of some DLT model. And once you have such kind of information, actually it's very helpful to study, for instance, what could be the essential skeleton. So as a result, we prove again that if X is strictly Calabi-Yau, so it's simple connected, and there is no higher cohomology of the constant sheaf. Then up to dimension 3, we know that I assume that the X is of the maximum degeneration type. So this is the type which the mirror symmetry people are mostly interested. And then we know that this skeleton is always is a homomorphism to S3 if I assume there is a reduced minimum model. And again, this reduced condition can be always achieved by a simple base change, of the base. Okay, now let's move to the SIM2 to study this kind of invariant which comes out originally from the oscillating integral. And now I want to give a new name of them. So basically now I call it a low canonical threshold. So this is just the lim soup of X and the pair CVF. So now the divisor D is just given by the valuation locus of this function F. And you can imagine when this number is very large, then because it's very singular, it's not a low canonical anymore. Then there is just a threshold to make this from low canonic to not low canonic. And that threshold we call low canonic threshold. And then there is a conjecture by Shortcroft to conjecture all this set satisfy the ascending chain condition. Actually, this is one conjecture which has been kind of famous among the bilateral geometers, and we kind of settle it. And I will give you a rough idea how we solve it. So when X is smooth, so because this is local, if it's smooth, I can just assume X is Cn. Then this ACC conjecture was actually proved by Delphinex, N, and Musata. But their proof is of a very local nature. And our proof is indeed we just reduce this kind of questions to global questions. So somehow from this point on, you will say that this kind of interaction between local geometry and global geometry plays a very deep role in both sides. So actually what we prove is so-called a global ACC conjecture. So the statement of the global ACC conjecture is a little bit technical, but next slide you will see how this global ACC conjecture implies this one. So basically, if this conjecture just say if I have a low canonical pair X delta, so which is low Calabi-Yau, so this condition just say it's low Calabi-Yau. So the K plus delta is trivial. And I assume the coefficient of my delta is inside a set I, which I fix at the beginning, but satisfy the descending chain condition properties. And then I just conclude there is a finite set I0 in I, such that all these kind of pairs, the coefficient of delta will be automatically in I0. So the key point is the choice of I0 doesn't depend on the X delta. So once you have this I immediately have this I0, and such that if I have a low Calabi-Yau, the coefficient set, if it's in I, it has to be in I0. So as I said, the proof of this, behind the philosophy is kind of local to global principle. I mean, in mathematics, I think there are lots of local to global principles. And in bilateral geometry, there is one. And roughly speaking, under this local to global principle, for chaotic singularities, it corresponds to Fano varieties. And if I have a strict low canonical singularity, so if I have a low canonical singularities which are not chaotic, then it corresponds to low Calabi-Yau. So remember, my low canonical threshold is a threshold which makes my singularity low canonical precisely at that point. So that's kind of just give you a strict low canonical pair. So that's why we basically, for that kind of pair, we can attach a low Calabi-Yau. And the way we attach it is based on this. So because it's a low canonical threshold, we can find the divisor which makes the singularities low canonic, but not better. So that just means there is a divisor which has this property. And now we can find a model Z mapped to X, such that this E is contained in this Z. So you can just think about this as I have this E. Now I just find another model which I only extract E. So this difference between Z and X is just along E. And you can just think E is mapping to a point. So now if I pull back this on this E, because E is mapping to a point, I pull back a linear system class from downstairs, and I restrict along E, it's trivial, because E mapped to a point. So I can first restrict my class to the point and pull back to E, it's trivial. On the other hand, because of this property, it has this kind of expression. So if I restrict this kind of expression to E, this Kz plus E to E, I just get Ke. If I apply a junction formula, I just got KE. And this divider, if I restrict on E, I just got a boundary. So out of this, I just got a low Calabi-Yau pair. So this is the way how out of a singularity, strict low canonical singularity, I get a low Calabi-Yau pair. And you can imagine if this number is increasing, like in ACC condition, if I want to prove it's stabilized, if it increases, then I just know that this number, when I restrict on this E, the coefficient along this divider is always also increasing. But remember, in our global ACC, we just say if it's increasing, it's of course DCC. But if it's DCC, it's finite. So let's just say I cannot have an infinite many different increasing sequence. This C has to stabilize. So then, if you translate that global ACC to this local, if you translate that global ACC, then we just know that this sequence of C has to stabilize. Then, which implies the lower kind of threshold has to stabilize. So this way we say that the global ACC implies the local ACC. But the question is how to prove the global ACC. And here actually there is a big circle of ideas behind here. So basically we actually don't treat low Calabi-Yau. We actually treat the general type. So what we want to prove is certain boundedness result for general type varieties. I think if you are in the ceremony of the first day, you heard that in Berka's work, he studied the boundedness of Fano varieties. The Fano is like minus k is ample. So here we basically study the opposite case, the kx is ample. And we basically prove a similar boundedness result. So here the boundedness result, the two technical statement is if I fix a DCC set, and if I look at the volume of kx plus delta, and then all these possible volumes, they actually satisfy DCC properties. So basically, if my coefficient is in a DCC, then the volume of the variety is also in a DCC set. And the second part is that there is a uniform n, such that the n x plus delta is birational. Here, the n only depends on the set of the coefficient set and also the dimension. So somehow, the relation between these two statements was first found by Chuji, and then it was based on Chuji's work. We realized that if we want to prove this, we have to prove them simultaneously. And the last thing I want to say is that actually this kind of statement is a key point to show that the KSBA moduli space. So this moduli space is named after Kolar, Schaffer, Baron, and Alexei. By the way, this conjecture is also called the Alexei-Kolar conjecture, because I think Kolar first asked this for dimension 2, and Alexei proved it, and then asked this for higher dimension, and we just settle the higher dimensional case. So basically, this conjecture, I think the reason Kolar asked this is because he wants to use it to settle the boundedness of the KSBA moduli. And actually, since we have this result now, we basically do settle the boundedness of the KSBA moduli in general dimension. But on the other hand, the effective number here are actually not known. I mean, I think if you go to Meng Chen's lecture tomorrow, you will hear in dimension 3, we know a lot of more effective result. But in general, the effective bound is not known. So now I want to come to the third theme, which I want to talk about the local to global principle between Fano variety and the chaotic singularity. I mean, I think in some sense this is the richest part of the correspondence between local and global. And actually, this correspondence between Fano varieties and chaotic singularities, this has been known for a long time. For instance, I think it also appeared in Berka's proof of BAB conjecture. But here, I want to concentrate on some very new perspective. And this new perspective only appeared in the last maybe 2 or 3 years, although people have studied this set of singularities for many, many years. So as I said at the beginning, this new perspective is I want to find a stability theory which plays a similar role as K-stability theory for final varieties. So if you were in Donaldson's talk, you know that this K-stability theory basically captures whether the final variety has a Kähler-Einstein metric or not. But it's completely algebraic geometry definition. And here we want to do something similar for KOT singularities. But for this reason, we have to introduce some more definitions. So now I start to look at the valuation space, which I basically look at all the valuations whose center is X. Now, because it's local, I just give a name X to be spec R. And I define the log discrepancy function. So previously, I defined discrepancy function. What I take is just +1, and then I just call it a log discrepancy. But I don't just define it along the divider. Actually, I define it along all the valuations. So this divider, that of course just corresponds to divisory valuations. And then I try to extend this, this definition to all the valuations. And because you know that the divisory valuations, after rescaling, indeed form a dense set in the space of valuations. So this can be done. But the crucial definition is by Chili. Actually, he is a complex geometer, so somehow his background is to study metric. But then he made this algebraic definition that the normalized volume of a singularity, of a KOT singularity, for valuation V here is just defined as the volume times the AX power to n. So because it's KOT, this number is always positive. And this number volume, actually it was defined before by Harry Smith, Lattice-field and Yin. But the main observation by Chili is that actually we want to normalize it. So somehow we actually put this too, and we times this volume by this number, the log distributed power to n. And basically the volume is just defined by the co-length of the growth of the co-length of the valuative idea. And actually what Chili proposes is that the minimizer of this V. So now because I define this function on this space, so I can look at the minimizer. And what he proposes is this minimizer actually carries a very deep geometric information. And this was formulated in this, we call it a stable degeneration conjecture. So the first, the conjecture contains many parts. So some parts was formulated by Chili. But to make the picture complete, we actually have, Chili and I, we proposed a couple of more conjectures. And now you put all the conjectures together, we call it a stable degeneration conjecture. So basically that's say, give a KOT singularity, up to ray scaling, there is a unique minimizer in this valuation space. First, the normalized volume is, it doesn't depend on the ray scaling. So if I rescale my valuation V to lambda V, the normalized volume is the same. So in other words, if I define normalized volume, I can always forget the ray scaling. Then I just say this minimizer is unique. And it's actually not just unique, it's quasi-monomial. So here, I'm not going to define what quasi-monomial is, but basically that's kind of the geometric valuations you can see. So it's more than, so divisory valuation is always quasi-monomial. But if you want to say valuations geometrically, quasi-monomial is, so far, is the best valuation we can see. Once beyond the quasi-monomial, I think we don't have that much geometric tool to study it. But actually, it's not just a quasi-monomial. It actually has finite generated associated gradient ring. This is very real. Even I start with a smooth point, I look at the valuations over a smooth point. Often the associated gradient ring for valuation is not finite generated. So, but somehow for KOT, we conjecture the minimizer always has a finite generated associated gradient ring. And then actually this, now if I put an X0, which is spec of the gradient ring, and my valuation will induce a vector. So because there is a gradient here, then there is a torus action on this X0. So once you have this torus action, you can talk about the Rayb orbit. And this valuation V actually will induce a Rayb orbit lambda V. And we actually conjecture this X0 lambda V is a K semi-stable final cone. So So here, the case semi-stable, so it's not a case semi-stable for final variety, it's slightly generalized it. So if you ask the metric question, whether a final cone singularity is case stable or not, corresponds to whether it has a Sasaki-Einstein metric. So somehow we generalize the Einstein metric to Sasaki-Einstein metric. Because if the lambda v is a rational vector, so then it will generate a C star action. If you take the quotient of the singularity by this C star action, you just precisely got a log final pair. And then the case stability of the log final cone is the same as the case semi-stability of the base, the log final varieties. But here, in general, the lambda v is not necessarily rational. So here, the case semi-stability is of the final cone is defined by Collins and Sacchilidi, which generalize the original definition of Tian and Donaldson a little bit from log final variety to final cone. And so, because of this, we want to give a name of this kind of valuation, which is quasi-monomial, finite generated, and which is K-semi-stable. We basically call it K-semi-stable valuation. So in other words, we just want to use the conjecture just say any minimizer gives you a K-semi-stable valuation. And this conjecture is actually strongly inspired by this study of metric tangent cone, which I think appeared in Donaldson's talk. So actually for this stable degeneration conjecture, we actually know many parts of the conjecture. First, we know the existence. So the minimizer always exists. When you think about this function, it's a function on a very complicated space. So the existence of minimizer is by no means trivial. And actually that was proved by Bloom. And then in a different generality, it's proved by Qili and Yuchen Liu, and Qili myself, and in the most general situation by Qili and myself. So we prove that the case stability, so a case stable valuation is always a minimizer. So remember the conjecture is minimizer is always case semi-stable. So in other words, now we prove case semi-stable is always a minimizer. So in other words, these two notions should be actually identical. And so in other words, now if you translate this back into the original conjecture, let's just say, given me a KOT singularities, there is a unique, very K-semi-stable valuation over it. So to degenerate your singularity into some like cone singularity with some like a K-semi-stable structure. I think this kind of conjecture, which has never appeared in bilateral geometry before people to start to look for the interaction between the subject of a minimal program and the subject of K-stability of final varieties. And the last part, Qili and myself, we proved that the unique, so we didn't prove the uniqueness among all the minimizers. We only proved the uniqueness among the K-semi-stable valuations. So in the second step, we already showed K-semi-stable is a minimizer. But just this, it already answered a conjecture by Donaldson and Sun affirmatively. Because in Donaldson and Sun's case, they construct some valuations out of metric. And because of their construction, their valuations is automatically K-semi-stable. And then what they ask is whether this valuation is indeed only dependent on the algebraic structure of the singularity, because their original construction uses metric. But because we show their construction is K-semi-stable, and the K-semi-stable valuation is unique, then of course, this valuation only depends on the algebraic geometry structure because it's unique. So actually, we actually can prove more. But the missing part is we cannot prove a minimized quasi-monomial. I think this kind of bilateral geometry question didn't really appear in the original study, at least in the bilateral geometry community. So if people study bilateral geometry, I really want to suggest you to look at this kind of questions, because it's very new. Actually, I don't know what kind of tools we need to study a valuation, to prove a valuation is quasi-monomial. And once we have this, Then we also don't completely know the associated rings finally generated. So we know for divisorial evaluation. So for divisorial evaluation to prove the associated ring is finally generated, that's a typical MMP statement. So somehow we actually do use the BCHM to prove this. But again, if my evaluation is not divisorial, it's of high rank. So what kind of tools we need to prove the associated ring is finally generated? That's not clear to me. So for the last slides, I want to go back a little bit to talk about the case stability of Fano varieties. So actually, I talk about, in the previous slides, I talk about the valuations over singularities. So, but actually, to use these valuations to study the case stability of Fano varieties, that also has a lot of fruit in the recent years. So actually, the original definition of case stability is not while the evaluation. It was while the degeneration of Fano varieties. But then, based on a bunch of people's study, now we can basically redefine only use evaluation. And this change of this view is actually very important because somehow it connects very well to the partial geometry. It connects much better than the original definition to partial geometry. So here I want to pose two guiding questions. So the first one is, give a Fano variety. We know it's case stable if and only if it has canal symmetric. Then, of course, we want to prove that some of them are case stable, and then conclude that some of them has canal symmetric. But how to do it is very difficult. Actually, then the second question is, actually, we definitely expect that using the case semi-stability, we can construct a projective moduli of Fano varieties. And but so far, I mean, if you look at the construction, there has 6 steps, and only like 1, 2, 3 steps of them are known results. But the main part are conjecture. But anyway, there is a lot of progress in both questions, and my time ends up here. Thank you very much.
Thank you very much for your clear lecture. So before I forget, if you have the app, you can download his file with the talk. So please, it's a good opportunity. So we have a few time for a few questions. Do you have any questions for?
Do you have some insight into the mixed Hodge structure of the link of an isolated singularity from the DLT model?
I mean, the first part, the dual comments basically capture the weighted zero part of for this structure. So somehow we basically give a geometrical realization of weighted zero part. But I think our approach didn't extend to other weighted parts.
I was curious because you said that though the model is not unique, any two models have the same canonical class. That suggests even the mixed Hodge structure is somehow captured.
Yeah, I mean, somehow that's true. I mean, we can say the weighted zero part. That's what. Yeah.
Any other question? Okay.
Maybe the question is irrelevant, but what makes you believe that valuations are quasi-monomials?
The valuation being quasi-monomial just means that the x0 has the same dimension as x. So somehow now, based on the examples we actually always say that there is a degeneration to some k-semi-stable singularity, which is of course of the same dimension. So that's why we believe it has to be quasi-monomial.
Okay, we thank the speaker again.